Okay, so this is a lecture that was mistaped last time, so I'm trying to give you the essence of the material in this clip. So the lecture is disconnected to what we had been doing before with the Fisher information. And so we take it from the top as follows. First, let's consider that omega here is the real system. Okay, so that's the structure at hand, right? That's the bridge, that's the building, that's whatever it is, but this is the real system. The real system is subjected to a number of inputs, which we can call U1, U2, and we will refer to the last input as UR, meaning that there are R inputs. This thing also has a number of outputs, and we will refer to the outputs as Y1, Y2, and the last output would be YM. So there are M outputs and R inputs, okay? R is equal to the number of inputs, and M is the number of outputs. In other words, the number of sensors that we are using to measure the response, okay? Now, the real system is what we refer to as infinitely dimensional. That is, there is no model without having infinite degrees of freedom that can provide an exact representation of the real system. Or, if you don't want to go with degrees of freedom, you have to say that this, because the mass of the system is distributed everywhere, this would lead to partial differential equations. Now, maybe I will do the following. I will do a small derivation right now of a treatment of the problem of dynamics, okay? Which, of course, this is not a course about structural dynamics per se. It's just that we need to do this background to get you where we're going. So imagine that you had a rod like this, right? That rod has an area A. A is the area, has a modulus of elasticity E, okay? And has a coordinate X that starts there, and this distance then is dx. And let's say that we apply some sort of stress at the end, whose resultant is, let's say, P, a function of time, but we apply it in a distributed way, right? This has density, rho, is the density of the material. So, again, I repeat, the reason why I'm doing this is that you can appreciate what a modeling of a system without lumping the masses in points and saying that there is a finite number of degrees of freedom leads to. So if we take a free body diagram of that piece there, we can say that on the right side of it, there is some stress. On the left side of it, there is some stress. We can call this one the stress at X. And in the same vein, that this would be the stress at X plus the partial derivative of the stress at X with respect to X times dx, right? And if we multiply times the area, we would get a force here, which is sigma X times the area. And we would get a force here resultant, which would be sigma X plus the partial of sigma X with respect to X dx, right? Multiply times the area. Now, those are the forces that way, the force this way due to the stress. In addition to that, there is going to be an inertial force, right? Because there is dynamics, this thing is vibrating under this P load. So there is an inertial force to the left here, which is the volume of this. And what is the volume of that? Well, the volume of that is what? The area times dx, right? That's the volume. So if we multiply it times the density, that would be the mass. And according to Newton, force equals mass times acceleration, according to Newton's law, right? And the acceleration of this is the partial derivative of u with respect to time, second derivative, where u is the movement of the points. In the x direction. Right? So remember, x is an axis that measures from here. But if we say u there is 0.01 inches, that means that at a given, let's say at some time, that means that the load has produced at that time a deformation there of 0.01 inches, right? So again, you look at this, so you say now sum of the forces in the x direction equal to 0. So if you say sum of the forces in the x direction equal to 0, you would say minus sigma x times a plus this, which is sigma x times a plus partial of sigma x with respect to x times dx times a, right? Those are the two forces. This one is coming to the left, so minus a times rho times dx times the second partial of u with respect to time, and all of that must be 0, right? So that equation is just equilibrium. The a's cancel. These two sigma x's cancel. That a went here. And then we have that I'm going to have to erase. So we have what? That the partial derivative of sigma x with respect to x times dx, right? Plus, no, not plus, minus this was minus, plus, plus, minus, right? So now we have minus rho times dx times the second partial of u with respect to time equal to 0, right? Okay, so that's what we have, and I can see that our dx also cancels. And so this equation just simply has sum of the forces in the x direction on this piece of the rod, right? Now, with that, we can then say, okay, but what is sigma x? That's just E times epsilon x, right? Young's modulus times strain. But the strain is the partial derivative of u with respect to x by definition. Therefore, we find that the partial derivative of sigma x with respect to x, that is this quantity, is equal to E times the second partial derivative of u with respect to x squared. If we then substitute in the equation, we would find that E times the second partial derivative of u with respect to x squared minus rho times the second partial derivative of u with respect to t squared is equal to 0. This equation, if we divide by rho, by E, gives us second partial of u with respect to x squared minus rho divided by E multiplied times the second partial derivative of u with respect to t squared is equal to 0. So if I wanted to consider the dynamic behavior of a rod that had a constant area and it was made of an elastic material, and I wanted to solve the problem exactly without giving it a finite number of degrees of freedom, I would have to deal with this equation that would have to be solved accounting for the boundary conditions, right? The boundary conditions being that at this point on the left, right, at x equal to 0, u is equal to 0, right? That's one boundary condition. And at x equals to L, if this is L, right, we know the stress there. So we can say that the stress sigma is equal to P as a function of time divided by A, because that's the applied load divided by the area, right? Assuming that it was applied as a uniform stress distribution. And since the stress is equal to E times the partial of U with respect to X, that's the stress, right? That would be PT over A. And so we find that the other boundary condition would be that the partial of U with respect to X at X equal to L is equal to P divided by A divided by E, right? So this is one boundary condition. This one is another boundary condition, and we would have to solve this differential equation. Now, this partial differential equation, this is normally considered too hard, right? So what we do is we replace the real system, right, by a model which is finite dimensional. In this case, it's like saying, okay, divide this rod into a number of segments, right? Lump the mass of each segment in a point, and then connect them with appropriate springs that represent the stiffness of the material. And therefore, what we're doing is replacing the rod with a model, that is a spring and a mass, another spring, another mass, another spring, another mass, etc., right? And as you can see, we could put as many masses as we wanted. The more masses and springs, the closer we would be getting to the actual rod, right? Now, after this dilution or departure from the main road for a few minutes, all I wanted to do with all of that was simply to say that the real system is infinitely dimensional. It's like the rod that leads us to the partial differential equation. We replace it mentally for discussion by a model. And that model is finite dimensional. That is, it only has a given number of degrees of freedom, right? Some number of degrees of freedom. The expertise, whatever it takes to be able to make that model, that's not the essence of this class. That is not something that we are here focusing on, but we have said that we will restrict our attention to models that are lump masses connected by springs. And for example, I will repeat something that I did because it probably wasn't recorded correctly before. So for a situation like this, these are the kinds of models that we will restrict attention to so that you can calculate the model or formulate the model basically by inspection. However, as I am doing this, I just recognize that I have to backtrack for a second. So this is the thing that is a model. Once we decide on the model, that model is described by a mass matrix, by a stiffness matrix, okay? Mass matrix, stiffness matrix, and also by a damping matrix. We have not in the class talked about damping matrices thus far, and at this point you don't have to worry about it. What you do need to know is how you can formulate a mass matrix from the sketch of the system and how you formulate a stiffness matrix. Once these matrices are available, the equations of our systems, which are linear, will always look like this. Again, remember, this is the model. Okay? And on the right side, we have a new term, B2, and this is the applied load. Now, I will explain by example, or illustrate by example, how the matrix M and how the matrix K are formed for the kind of system that we are happy to limit our discussions for, in order to be able to focus on what the topic of the class is more readily. So here, let's say that this mass is M1, this mass is M2, this mass is M3, this mass is M4, and this is the first coordinate, the second coordinate, the third coordinate, and the fourth coordinate, okay? Q1, Q2, Q3, Q4. Let's say that we name the springs K1, K2, K3, K4, and K5. Then, by inspection, well, not by inspection, but we just simply remember that K, I, J are the forces that hold the system at Qi equals let's see, how do I say it more clearly? K15 force that I due to the load. Okay. Qj equals to 1. Forces that hold the system at Qj equal to 1 are all the Kij's. So it's the force at 1 due to Qj. I don't know, I wanted to do a general and I didn't say it as cleanly as I wanted. So Kij, let me write it like this. Force at I, okay, due to unit displacement at J. Qj equal to 1, other Qj's, no, other Q's, QL equal to 0 for L not equal to J. Okay, I guess that's clear. So Kij is the force at I due to Qj being 1. I don't know what this was here. When QL is equal to 0 for L not equal to J. Okay, so I will come back to that definition in a second, and hopefully you already know this. But anyway, the mass matrix for our case is trivial. It's just a listing in a diagonal of the masses. So this would be M1, M2, M3, M4. That's the mass matrix. The stiffness matrix can be obtained from the definition by inspection. So I will not draw it because I think it's simple enough. if coordinate 1 is given a unit movement, you can see that coordinate 1, if we move it forward by a unit amount, is going to be pulled to the left by K1, is going to be pushed to the left by K2, K1 times 1, K2 times 1, and it will be pushed to the left by K5, right? Because this spring is compressed, this spring is compressed, this spring is compressed. Then we simply say that the force there is K11. And so we see that K11 is equal to K1 plus K2 plus K5. So we have K1 plus K2 plus K5. Now, what is the force at 2? This is M1. If you look at mass 2, you can see that in mass 2, when we move this one, we have a force pushing it that way, which is K2 times 1, right? And I guess that's everything. So this would be the force at 2 due to a unit movement at 1. And from there you can see that K21 is minus K2, right? The third mass, which is over here, would be subjected to what? This is the one that moved, so this is in compression. That's pushing this point to the right with K5. And this is K31. And so we find that K31 is minus K5. And if we look at mass 4, we see that mass 4 is not being pushed by anybody when we move degree of freedom 1. So we find that K4 due to 1 is 0, right? Now that procedure we apply by moving every mass one at a time and keeping all the others in place. So by inspection, and you can convince yourself as an exercise, I will now move 2, and I will see right away that 1 is being pulled to the right with K2, and so it's minus K2. That in order to move this one, I need to push K2 plus K3. That in number 3 I get minus K3, and in number 4 I get 0, right? Now when we move 3, we see that to move 3, when we move 3, what happens? We get minus K5 at 1, right? We get what at 2? When we move 3, we get minus K3, right? And in itself, we would get K3 plus K4 plus K5, because remember, nothing moves except itself. So we get K3 plus K4 plus K5, and in 4 we get minus K4. And then finally, when we move K4, we get nothing in 1, we get nothing in 2, right? We get minus K4 in 3, minus K4 in 3 and K4 in 4. So that is the stiffness matrix for that structure, okay? Notice, I repeat, that all that we are doing is applying that definition. Kij is the force at I due to Qj equal to 1. When all the other Q's are 0, that plus basic simple statics gives you that. Notice that the matrix is symmetric, right? I was just calculating it every time for the sake of not jumping to the fact that it was symmetric ahead of time, and you can see that the matrix turns out to be symmetric. We will not require procedure to calculate the damping matrix at this point, so I will not dwell with it, okay? So that means that we are in a situation where, in order to not be burdened by difficulties on establishing what are the matrices of the system, we will be looking at systems that are simple like that, connection of mass dampers, masses connected by springs, and perhaps we'll push dampers some later on. but we'll deal with that when we get there. So the equation of motion is mq double dot plus c damping q dot plus stiffness matrix times q b2 ut. I've already discussed M, I've discussed K. I said you don't have to worry about C dam right now, so I need to say something about B2. Again, B2 is most easily illustrated by example because it's such a simple idea. So let's say that your system was like this. It's a stack with degrees of freedom 1, 2, 3, 4, and 5. Okay? Now let's say that the applied load was a load over here that was 5 sine of 3t. That was another load here which was 10 sine of 3t. And let's say there was another load here which was 2 cosine of 2t, for example, right? So, sorry. In this case, we say that B2 is a matrix that has, again, this matrix is n by n, where n is the degrees of freedom, so it's this one, so is this one. And this one is n by r, where r are the number of inputs. But what we should say is that there are a number of different input time histories, not physical inputs. In this structure, you can see that I have 3 places where I have inputs. But these 2 inputs are both sine of 3t. So actually, when I want to describe that input, I just say that input is not applied at 1. In level 2 has a 5. In level 3 has nothing. In degree of freedom 4 has 10. In degree of freedom 5 has nothing. The next input has nothing except in 5, which is 2. And so that would be my B2 matrix, which would then be multiplied by what? To get the loads. It would be multiplied by sine of 3t and by cosine of 2t, correct? Right? That would be the right-hand side of the system of equations. So that's how you get B2. Now, if I wanted to, right? If I wanted to, if you understand basic linear algebra, right? You could, if you'd like to, you could have put the 5 here and called this a 1. And then this could have been a 2, right? And you could have put the 2 here, and this would have been a 1. So this drawing here, 5 sine of t, 2 cosine of t with a matrix like that, is exactly the same thing as before. Okay? So B2n could be this, or it could be the one before. The results for everything we will discuss are exactly the same. Right? Okay. Now I am going to check, and I'll make this in 2 parts because I want to check that the taping is being done correctly.